Hey, good evening, everyone. Welcome to O-Level Physics lesson. My name is Mr. Chu. Today is Monday, 29th of May, 2023. Okay, and today we will be starting on the topic on pressure. Today we'll be covering the theory, and then the next 2 to 3 lessons will be going through past year question. Okay, so pressure. Okay, so what are we going to learn in the topic of pressure? So let me share with you all, let me show you all the syllabus. Do you actually study the syllabus or you all do not do that at all? Okay, so as you can see over here, okay, this is what you need to know for this topic. Okay, for this topic, you need to know there's two parts, pressure and density and fluid pressure. Okay, so the first part here, pressure, okay, we'll be talking about normal pressure itself. Okay, normal pressure. Okay, so we're going to talk about how do you determine pressure based on the force and area. So when there's more force, definitely you see more pressure. When the area is reduced, okay, you also see more pressure as well. Okay, so from here you can see the formula that you all need to know is pressure is equal to force over area. Okay, so this is the formula that you need to remember in this topic. Okay, pressure is equal to force over area. Okay, so from this formula, if A is a constant, if the area doesn't change, the greater the force, the greater the pressure. Can you see that? If area remains constant, the greater the force will result in a greater pressure. Okay, so in that sense, we can say that pressure is directly proportional to the force applied on it. Okay, I repeat myself again. Pressure is directly proportional to the force, okay, applied on it. Okay, so when force goes up, pressure goes up. Okay, can you see from this formula that is the relationship? Okay, the direct proportion relationship. Okay, likewise, if you have a constant force, your force is the same. Okay, that force could be your weight. Okay, you are one person. Okay, but you wear different type of shoe. Some shoe have big area, some shoe have small area. So if you are the weight, okay, standing on the ground with a different area, the bigger the area, the smaller the pressure. Can you appreciate that? Whereas given the same force, the smaller the area, the greater the pressure. So how are these two variables related? So if A goes up, P goes down, or if A goes down, P goes up, they are inversely proportional. Okay, so you can say that pressure and the area are inversely proportional to each other. Okay, so when I talk about this, are you able to appreciate, okay, what you all learn in Sec 2? Okay, the F equal to Kx and F equal to X over K over X. Okay, this is what you all learn in Sec 2, direct proportion and inverse proportion. Okay, and then we are applying that to physics. Okay, the direct proportion and inverse proportion, you all learn that in Sec 2 mathematics. Okay, this is what you learn in Sec 2 mathematics. So can you see? P and F, they are directly proportional. P and A, okay, they are inversely proportional. Okay, are you able to appreciate what this direct and inverse proportional thing? Okay, if you can appreciate, give me a yes reaction. Okay, give me a yes reaction. Nobody. Okay, thank you, Rui Hong. The rest of you, any reaction? Thank you, Hao Ming. Si Xuan and Chen An, are you okay? Thank you, Chen An. Si Xuan, do you know how to use the reaction on the Zoom? Okay, so let me continue. Okay, so are you able to understand the concept of pressure? Pressure is different from a force. Force is a directional variable. It's like you're pushing or pulling, there's a direction. Whereas pressure is nothing to do with force. It is just another term to measure. Okay, so basically pressure is a measure of how a force can change the shape of an object or body. Okay, I repeat myself again. You can, in layman term, you can say that pressure is a measure of how a force can change the shape of an object. Okay, that is a layman term of explaining pressure. Okay, in if the school or your exam asks you what is pressure, okay, so the way to define pressure is like this. So I'm going to type it out. You all actually, can you all just write it down and then type it in the chat and show me. Okay, so pressure is the force F acting per unit area A. Okay, pressure is the amount of force acting per unit area. Okay, per unit area. Okay, so can all of you type this out now in your chat? Pressure is the force acting per unit area, which is this formula. Pressure is a force per area, right? But in this case, I want you to write down the word per unit area. So can all of you type this out in the chat and show me? Okay, I'll be asking this as your I'll be asking this as your checkout question. So can everybody write down? Pressure is the force acting per unit area. Can all of you write that down now? Okay, very good, Rui Hong. Very good, Hao Ming. Well done, Si Xuan. Si Xuan, so have you learned this in the school so far? Okay, last one. Chen An, where is your definition? Okay, well done. Okay, so I want to see this per unit next time when you write down. Just like what is the definition of velocity okay, or anything that is got ratio one, you just put per unit. Okay, just like I give you an example. What is the definition of okay, later I'll give you a definition later. Okay, so are you clear about this? So this is a very simple way of calculating pressure, and most of the pressure on solid, okay, we'll use this formula. Okay, let me go through the units. Okay, force, the unit for force is Newton. The unit for area is meter square. So what is the SI unit for pressure? Okay, you can tell me Newton per meter square, that is nothing wrong. Okay, but this whole formula, this whole unit is also being replaced or substituted by another scientist name. Okay, we call him Pascal. Okay, so the SI unit of pressure is Pascal. Okay, so you can say that 1 Pascal is equal to 1 Newton per meter square. Is that clear? Okay, so the SI unit for pressure is Pascal. Okay, just remember that. Okay, next thing I'm going to share with you is this. Is pressure scalar or a vector? So can you make a guess? Is pressure a scalar or vector? Can you make a guess? Write down in the chat. Hao Ming tells everyone is a scalar. How about the rest of you? Is pressure a scalar or a vector? Chen An, Si Xuan, Chen An guess scalar. Rui Hong say scalar. All say scalar. Okay. Why scalar? Okay, actually you are right. Okay, the pressure is a scalar. It actually does not have a single direction. Okay, pressure acting on certain place, okay, acts in all direction. Is that clear? So for example, in the water, okay, what is the pressure of this point here in the water? Okay, the value is the same applying in all direction. So the pressure acting on this point is in all direction. Okay, so therefore pressure has no direction and pressure is a scalar. Okay, so can you all remember that? Okay, so pressure is capital P, not small p. The SI unit is Pascal. Okay, the formula is force over area or force per unit area. That's the definition. And pressure is a scalar. Up to here, is it very simple? Okay, if you understand, give me a yes reaction up to now. Okay, how many are you okay? Okay, so the next thing I'm going to talk about will be hydraulic system. Okay, just this one. Okay, I will skip this for now. Later, I'll talk about this later on. Okay, so I'll skip part C for now. So we will just talk about density first. Okay, so what is density? Okay, density in this over here, the formula is mass over volume. Okay, so based on what I teach you about the definition of pressure, can you all tell me what is the definition of density? Okay, density is what? Okay, based on this formula, can you describe? Okay, define density. Exam question is define density. Okay, pressure is the amount of force acting. Okay, amount of force acting per unit area. Am I right? So density, you know density, the formula is mass over volume. So now I want all of you to define what is density based on the same way I teach you how to define pressure. Okay, maybe I will just rewrite here again. Pressure is the amount of force acting per unit area. Okay, so now I want you to use the same idea. Tell me what is the definition of density. Can everyone do that now? Okay, pressure is the amount of force acting per unit area. So can you tell me what is the okay, Ray Hong, well done. In this case, no need to write down the word acting. Okay, but write Ray Hong, well done. Okay, minus the word acting, you'll be fine. Chen An, you forgot the keyword here. Try again. Okay, Chen An, well done. You got it correct. How about Hao Ming and Shi Xian? Okay, if you are not sure, please ask for help. Okay, Shixuan, your definition is explained well, but that will not be what I'm looking for if the teacher asks you to define density. Okay. Okay, how many well done? You do just need to remove the word in. Okay, so Shixuan actually describe what is the meaning of density. Okay, and I think it's a very good way of explaining. Okay, Shixuan mentioned that density is the measurement of how tightly material is packed together. Okay, that is a very good way of explaining. But in exam, you do not need to define that way. Okay, but what Shixuan explained is exactly what density is about. Density is actually how packed, okay, how packed a substance is. Okay, I repeat again. Density is actually how packed a substance is. Okay, but in exam, I do not need you to write that way. Okay, I want you to write like this. Density is the amount of mass per unit volume. Okay, so that will be the actual definition of density. Okay, that is required of you when you write that down in exam. Okay, and let me just write this formula here. Density, the short form or the symbol for density is this symbol, rho. Okay, it's pronounced as rho. Okay, density is equal to mass over volume. Okay, mass is a small letter m, volume is a capital V. Okay, so why do I say density is a measurement of how packed and substance is? Okay, let's go through this again. If a volume of the thing is the same, there's two things here. Two volume is the same. In the first one, I pack in 100 atoms. Second one, I only pack in 1 atom. So the mass of the first one is bigger. So it's more packed. So the density is higher. Okay, I repeat myself again. Given the same volume, okay, the same space that it occupies, if it contains more mass, in this case 100 atoms, in the same space, compared to another one with just 1 atom in the same space, the one with 100 atoms in the same space will have a greater density because there are more atoms packed together. Is that clear? Okay, so this one has a greater density. So using the Sec 2 mathematics, can I say that if volume is a constant, density is directly proportional to the mass? Can I say that? If volume is a constant, the greater the mass, the greater the density. So there's a lot of mass packed in the same space, in the same volume. The density will be greater. Are you convinced about this? Likewise, now we have the same mass. Okay, let me redraw. We have the same mass, 100 atom, 800 atom. The first one has a big volume. Second one, small volume. Okay, same 100 atom packed into 2 different spaces. The first 100 atom is in a more spacious place. Okay, so can you expect that they are less packed? So density will be lower. Whereas the same 100 atom is packed in a smaller space, a smaller volume. Okay, so can you expect that the density of this is actually greater? Can you see that? Okay, so if the mass is the same, the greater the volume, the smaller the density, the less packed the substance is. Can you appreciate this now? Okay, likewise, the same 100, okay, the amount of matter in this body, 100 atom, the 100 particles here, packed in a very small volume, a very small space. Okay, this V is very small, the M is constant, and therefore your density will be much greater. Okay, so what's the relationship between density and volume? If the mass is a constant, density is inversely proportional to the volume. Are you all clear about this? Are you able to appreciate what I'm trying to guide you all? Okay, I'm trying to make things a bit clearer to you all, and so that you understand rather than need to memorize. Okay, so far? Okay, next thing I'm going to talk about will be the symbol. Symbol for density is rho. It looks like this. Okay, so can I ask you? Density is how packed a substance is. So can you make a guess? Density is a scalar or a vector? Okay, density is a scalar or a vector? Okay, can you tell me? Okay, so far, how many you're right? Rui Hong, you're right. Chen An, you're right. Okay, so how packed a substance is there any direction? It's like how packed you are. And how packed you can pack your bag. So is there any direction to that kind of measurement? Okay, so for density, okay, it is a scalar. Okay, because how packed a substance is has no direction. Correct? It's just like mass. Mass is how much matter are there in the body. There is no direction. So how packed the substance is also has no direction. Can you appreciate that? Or you all cannot understand? Okay, so this is a scalar, not a vector. Okay, number 2, we're going to talk about the SI unit. The SI unit for mass is kg. The SI unit for volume is meter cube. So can you tell me what would be the SI unit for density? Can you all type it out in the chat? What is the SI unit for density? How many incorrect? The K must be small letter. Okay, this is a small letter, not a capital letter. Okay, write down again. Okay, the SI unit for density will be just this one over this one. So can you tell me the answer now? Chen An, Rui Hong. Okay, Rui Hong, well done. Chen An, well done. Okay, so the SI unit for density will be kilogram per meter cube. Okay, but however, you can ask me, how come in chemistry, all the substance that are given to you are all in gram per cm cube? That is also not wrong. But the SI unit is kilogram per meter cube. Okay, gram per cm cube is also a unit for density, but that is not the SI unit. Okay, the SI unit for density is kilogram per meter cube. Is that clear? Up to here, if you are okay with me, give me a yes reaction. Thank you, Chenan. If you are not okay, give me a no reaction so that I can help you. Thank you, Hao Ming. Thank you, Si Xian. Thank you, Rui Hong. Okay, so we are now done with density. Okay, we all know what is pressure. We don't know what is density. So now we are going to the last part, the last important part of this topic, which is the liquid pressure or the fluid pressure. Okay, so let me clear out everything. Okay, so we're going to talk about fluid pressure now, and we are going to let me try to derive, okay, how to find the formula of this thing itself. Okay, so before we continue, let me write down first. Pressure is force over area. Density is mass over volume. Okay, so for fluid pressure, okay, fluid pressure, how are we going to find what is the fluid pressure? Okay, so for example, I have a column of water here. Okay, inside is all water. You want to find how much pressure the water is, or this fluid is acting on this point. Okay, you have to find how much pressure, okay, at this point, which is actually based on the amount of fluid above it. In this case, it is the liquid. Okay, so first of all, okay, we all know that pressure is force over area. So in this example, how can we find the force? Can we find the weight of all the liquid in this column? Okay, so can I use the force? I change it to weight. Okay, weight. Yeah, I change it to weight. And then in the previous topic, we learned that weight is mass times gravitational field strength. Okay, are we okay so far? Okay, then we know that mass times G over A is the pressure. A will be the area here. This is A. And so now we are trying to find the weight acting on it. So this is the weight. Weight is mg. Now we go back to this. Can I substitute m equal to density times volume? Can we do that? Okay, so my m in this case, let me show you. This m is equal to density times volume. So my pressure now is density times volume times G over A. Can you see that? Okay, so my M is the same as density times volume. Is that clear? Now, we have the volume of all the water here. We have the area at the base here. So volume divided by area, what do we get? Okay, what do we get when we have volume divided by area? Okay, volume divided by area. Okay, is it the same thing as height? Okay, so I'm just trying to derive the thing to y'all. You're going to memorize. Okay, so you just need to know that when you talk about fluid pressure or liquid pressure, okay, the formula will be pressure is equal to H rho G. Okay, the H comes from the V over A. The rho is the density of the liquid above it or the fluid above it. And then G is the gravitational field strength. Okay, so I'm just trying to show you how I actually derive the formula of a pressure due to a fluid. Is that clear? Okay, so height of column is H. Density of the liquid is rho, and then gravitational field strength is G. Is that clear so far? Okay, so I'm actually using H rho G, okay, to actually measure liquid pressure. So in a real fluid, it's very hard to go and measure the weight. Okay, very hard to measure the area. Am I right to say that? Okay, but it's very easy to measure the height. Okay, the height, it's very easy to know the density, and then G is actually a known value. Okay, so from H rho G, we can easily find the pressure due to the fluid. Is that clear? Because W over A, these two variables, is very hard to determine in a fluid. How are you going to measure the weight of the fluid? Not easy, right? How are you going to find the area here? Also not easy. Okay, so we actually manipulate the formula, and therefore it came out this formula, H rho G. All you need to do is to find the height above the liquid of height above it, times its density, times its G. You will find the pressure due to the liquid above it. Is that clear? Everything okay? Okay, so this whole topic, you need to know three formula. First, pressure is force over area. Density is mass over volume. And finally, fluid pressure is equal to H rho G. Okay, so these are the three concepts that you need to remember and understand. And I will actually try to make you understand how these three come about. Okay, so far, is my lesson helpful? Okay, if it's helpful, give me a yes reaction. If it's not helpful, give me a no reaction. Okay, so give me some feedback. So far, am I able to give you a clarity about this topic? Thank you, Hao Ming and Ray Hong. Sishan and Chenan, are you okay? Thank you, Sishan. Chenan, are you all right? Okay, so I will go through some notes, okay, to cover the rest of the thing. It's very hard to explain without anything here. So I will go through the notes about hydraulic system. Okay, I will talk about how the height of a liquid column is used to measure atmospheric pressure. And lastly, how to use a manometer. Okay, I'll use the notes to help me. But the rest, A, B, D, and E, are you all very clear about A, B, D, and E? Okay, this is the very basic that you need to know. C, F, and G is a little bit on the second level. Okay, but on the basic level, A, B, D, and E, I hope I make things very clear for you all. Okay, so let me go to some notes to show, to explain clearer certain concepts. Hold on for a while. Okay, so let me show you some notes. Okay, so let me talk about this density thing. Density is the mass per unit volume. Okay, I mentioned that before. The SI unit is kilogram per meter cube. That's the formula. Okay, that's the formula. Okay, gram per cm cube is also not wrong, but SI unit is kilogram per meter cube. Okay, and okay, let me share about something about density itself. Every pure object has a fixed density. Okay, so if you want to compare and measure whether something is pure or not, you just need to find out whether, find its density and determine whether is it the same as the reported value. So let me give a very common example. Okay, the density of water is 1000 kilogram per meter cube. So 1 meter cube of water has a mass of 1000 kg. Is that clear? Okay, so I'll give another example of a okay, the other thing that you need to also know that is used quite often will be the density of mercury. Okay, the density of mercury is about 1,3,5,4,6 kilogram per meter cube. Okay, so this is something that you need to know. Okay, the density of mercury is about 13,500 kg per meter cube. So 1 meter cube has this amount of mass in it. Okay, that's for the density of hydrogen. So all hydrogen has the same density. All water has the same density of 1000 kilogram per meter cube. Okay, why I use hydrogen? Why I use mercury is because later on when we talk about liquid pressure, we're going to talk about this we're going to use this quite often. Okay, quite often. Clear so far? Okay, next thing. And why we use hydrogen? Sorry, not hydrogen. Why we use mercury to measure a lot of things is because at atmospheric pressure and temperature, meaning that in our normal environment, mercury is the densest liquid, okay, in our common environment. I repeat myself again. We use mercury in quite a bit of things, okay, because it is the most dense liquid, okay, in our environment, in our atmosphere. Is that clear? It's the most dense. It is 13 times more dense compared to liquid water. Clear so far? Okay, so another example, let me share with you. What other example which is, okay, gold. The density of gold. Okay, is 19300 kilogram per meter cube. So can you imagine? Okay, and this is the same as 19.3 gram per cm cube. So can you imagine you have a cube. There is 1 cm throughout. A gold bar, a gold cube will have a mass of 19.3 gram. Whereas for water, a 1 cm or ice, okay, ice, 1 cm cube of ice will be about 1 gram. So gold will be about 19 times more massive or more dense compared to water. Okay, is that clear? Okay, so this is the density of gold, density of mercury, and density of water. And all these value for the pure substance will all be the same. Okay, given the same atmospheric pressure and temperature. Of course, when the temperature changes or the pressure changes or the temperature changes, this value might change a bit. Okay, because when you heat up something, the volume becomes bigger, right? So the density will drop slightly. Okay, but the amount of substance should be the same. The density should be the same for the same pure substance. Okay, if someone tell you that this substance is water, but it doesn't come out to 1000 but only 500, then you can tell them confidently that what you are getting is not water. Are you clear about this? So for every pure substance, okay, the density is all constant, is fixed. Okay, so far? Okay, so I'm not going to share with you how to measure density. First, you measure the mass using your balance. Then you measure the volume. Then from there, use the formula, you get the answer. Okay, very simple. That's how you measure the density. Okay, then if something is more dense, it will sink. If something is less dense, it will float. If something is equally dense, you'll be at the same height. Is that clear? Then, if those who have learned thermal physics before, okay, you have learned thermal physics. Let me talk a bit of density. Let me touch on thermal physics. Okay, about convection. Have you all learned convection before? Okay, so convection, we talk about fluid. Convection only appear in fluid. So number one, when you heat up something, what happened? When you heat up something, it expands, correct? When you heat up, it expands, it means that the volume goes up. Is that clear? Then your density is equal to mass over volume. The mass remains the same, but your volume goes up. It takes up more space because it expands. What happened to your density? The density will drop. Is that clear? So when you heat up something, the object expands, the volume increases, the mass remains the same, the amount of substance remains the same. If it's 1,000 atoms, it's still 1,000 atoms, it still remains the same. The density will drop. So when the density drops, therefore, we have this thing called hot fluid rises. Because when it's less dense, it is on top. Okay, when it's less dense, it's on top. So hot fluid rises. Okay, so those who are learning the thermal physics on the convection, okay, where fluid can move, when you heat up the fluid or when the fluid get heat, okay, it will expand, the volume increases. When the volume increases, density drops. And when density drop, become less dense, it will rise. Are you clear about this? Okay, so for Sishan, you have learned this in thermal physics. Am I right to say that? Yes or no? Okay, so the other way around goes, is true. Okay, the cold fluid will sink. Is that clear? So it's like we learned before, hot air rises, cold air sinks. Okay, that's the reason why. Because when your volume changes, your density will change. And when your density changes, if it's less dense, it will rise. If it's more dense, it will sink. Is that clear? Okay so far? Any question for me? Can I? Okay, let's go into pressure. Okay, so let me talk about Pascal principle. Okay, you all need to know as Pascal principle. Okay, Pascal principle says that if pressure is applied to an enclosed fluid, the pressure is transmitted equally to all other parts of the liquid. Okay, so what does this mean? Okay, let me see whether there's any example here. Okay, so can you look at this liquid number 2 here? This liquid, first of all, you use a compressible liquid. So can you see that it's totally enclosed? When it's totally enclosed, okay, when it's totally enclosed, the pressure throughout this liquid would be the same. Is that clear? When it's enclosed, the pressure at X and at Y will be the same. Clear so far? Yeah, so it's totally enclosed. Can you see it's enclosed? There's no exposure to the air and so on. So when the liquid is sealed up and closed, there's no air gap, and the liquid is a non-compressible liquid, the pressure throughout this liquid will be the same. Clear? Okay, so this is a very important concept because we actually apply in this thing called the hydraulic press. Okay, in the hydraulic press, we make use of this concept where pressure at X is equal to pressure at Y. Okay, these two pressure is equal to the same. Okay, so how do we actually apply this? Okay, so because pressure at Y is equal to the pressure at X here, can you see that? The pressure at Y is equal to pressure at X here. So I expand the formula. I'll have force Y, force going up over AY, which is area of this piston, is equal to the force going down over the area X here. Is that clear? So can you see? Because the area of Y is greater than the area of X. Okay, this Y is greater than area of X. Okay, a small force applied on X will produce a big force that is strong enough to lift a car. Are you clear about this? I'll give an example. If this is 1 meter square and this is 10 meters square, can? So my X is 1 meter square. My AY is 10 meters square. I apply a force. Okay, let's say I apply 100 Newton force, which is about 10 kg of weight of mass. Okay, correct? Okay, 100 Newton force. So if my force on top here is 100 Newton, so my pressure will be 100 Pascal. Is that clear? And because this is an enclosed fluid, the pressure at X will be the same as the pressure at Y. Okay, that is the Pascal principle. So pressure at Y will also be 100 Pascal. Is that clear? And because the area at Y is 10 meters square, my force here would now actually become 1000 Newton. So this force that's pushing up is 1000 Newton. So can you see this magic here? 100 Newton of force pushing down can result in 1000 of force pushing up. Did we just created additional force? Is this something magical? Is this possible? Have you seen the hydraulic press before? Those that you actually press down, then the car you go up. Okay, that is a principle. Inside, we have an enclosed fluid. Where you press down, the area is small, so a small force can produce a greater force. Are you clear about that? So, my next question for you is this. Is force magically produced? Is there any downside to this? Okay, if 100 Newton can produce 1000 Newton, then might as well we make this even bigger area. I can make it 100 meters square, and then my force will become 10,000 Newton. By theory, you can actually create a much bigger force. But what is the downside? Can you think about it? Is there any downside? Or the force is just magically magnified with no downside at all? So can you think about it? What is the catch here? All I need to do is play the area, right? If the area is 10 times bigger, my force will be 10 times bigger. So I want to create a very big force. I just make my area much bigger, or this area much smaller. Yes, it works, but is there any catch? Think about it. Is there any catch? Think about it. Any catch at all? So if there's any catch, what is the catch? What is the catch? If you cannot think of it, just say help. Then I'll help you. So what is the catch? So to actually leave something that is very, very massive, we just need to play the area. So 10 times bigger area can produce a 10 times bigger force. So is there any catch here? Can you think what's the catch? You all give up? Okay. So you can actually create a much bigger force. Just need to play around the area. But what is the catch here? Okay, can you see down here? For you, I can make this area very big. Okay, very big. Okay, 10 meters square. Can? Down here, the area is 1 meter square. For it to move up 1 meter, I need to add in 10 meter cube of liquid. Is that clear? For the Y to go up by 1 meter, okay, the area times the height will be the volume. I need 10 meter cube of liquid to push it up. Clear so far? Then on the left side, okay, I need to push down 10 meter cube of liquid. And because my area here is 1 meter square, I need to push down 10 meter in. Okay, so I need to push down 10 meters. So this piston must go down 10 meters so that the piston 2 can go up 1 meter. Is that clear? And that is the catch. Clear so far? For you to lift up a big force, you must push down a lot of distance. So therefore, can you imagine when you need to jack up a car, the person jacking up the car, right, must press down many times only for the car to go up a bit. Are you clear about this? So you are sacrificing your distance to produce a greater force. Are you clear about this now? So do you understand the catch? Okay, it's just like a lever. You all know the lever? Okay, let me show you the lever. Okay, you have a lever here. You have a lever. Okay. You want to lift a stone, a very heavy stone. The longer the lever, the easier for you to push up the stone. Correct? Okay, so the longer the lever, you need less force to lift up the stone, but the distance for you to push down is much bigger. The stone only go up a bit, but your force that push it down is much more. Same theory. Okay, this is like the hydraulic press is just like a lever. Okay, you need a small force, but you must push down a greater distance just to lift a greater force. Okay, just create a greater force by moving a smaller distance. Are you clear about this? So are you able to appreciate this hydraulic press now? Okay, with a very small force, you can actually create a greater force, but you need to push a much bigger distance to lift a small distance. Clear so far? So nothing is being created magically. Okay, the catch or the drawback is the distance is much more. Okay, because the volume is the same, 10 meter cube. But to move 10 meter cube with an area of 1 meter square, you need to push down 10 meters. Is that clear? Okay, so this is the hydraulic press. Are you able to appreciate the hydraulic press now compared to last time? Did I have to explain clearly? If so, give me a clap reaction. If you already know, give me a yes reaction. So Chen An already know. Si Xuan already know. Nobody give me a clap reaction. So sad. Okay, let me continue. Okay, so we talk about fluid pressure just now. Okay, so for our at sea level, the amount of gas above our head all the way to the end of atmosphere, we call it the atmospheric pressure. Okay, so for example, at the sea level, this is sea level, there's a lot of air on top pushing down on you. So all the weight above you, above the sea, okay, they are actually air and they also have weight. So there's force pressing down on you. So this pressure, we call it atmospheric pressure. The higher you are, whether you're in a mountain, let's say Mount Everest, at the top here, there'll be less air above you. So the atmospheric pressure at the top of the mountain will be lesser. Is that clear? Ken? Okay, so I'm going to teach you another thing. Now, this is not an enclosed liquid because the liquid here is exposed to the air. Can you see that? This liquid here is exposed to the air, so I don't call this an enclosed liquid. Okay, whereas this one is enclosed because it's not exposed to the air. So in a hydraulic system, the liquid is enclosed. So everywhere along this liquid has the same pressure. But when it's not enclosed like this, you cannot use the Pascal principle. Okay, you use another principle. The other principle that we're going to learn is this. Okay, so for liquid pressure, okay, anywhere along the same line will have the same pressure. So can you see here? I draw from A to C. So the pressure here, PA, is the same as the pressure here, PA, which is the same as the pressure at B. Is that clear? So at the deeper area, deeper here, there's liquid above there's liquid between the line and this point. Am I right to say that? So the point here will have a greater pressure than the red line because there's an additional liquid above it. Understand now? So in a liquid or in a fluid where it is not enclosed, anything on the same line has the same pressure. Understand so far? Okay, so you are convinced already. I'm going to draw 3 points. Point A here, point B here, and point C here. So these 3 points has the same pressure. Clear so far? Because they are all on the same horizontal line. Okay, so PA, I can say that this is the atmospheric pressure because this point here, the pressure on A here is due to all the atmosphere pushing it down at this point, at this line. Are you convinced? So this pressure A and this pressure A here has the same pressure, okay, and they are all due to the atmosphere on top of it pressing down on the liquid. Clear so far? And we are convinced that PA is the same as PB because they are the same line. Okay, so PB, the pressure at B is due to all the fluid above it. So what are all the fluid above it? Let me highlight to you all. All the fluid above it will be this part here. Can you see? And then on top here, it is vacuum. Means there's no air inside. So there's nothing pressing down. Here is nothing at all. So all the pressure at B is due to the pressure of the liquid above it. Is that clear? So if I can measure the liquid above it, can I actually use that to determine the atmospheric pressure A here? Can? So now, can we revise? Revise, we use P. We assume this is P, is 10130 Pascal. Can? One more zero. 101,300 Pascal. And if I tell you I'm using this liquid I'm using is mercury, and just now I tell you the mercury density is how much? The mercury density is 13546 kilogram per meter cube. So based on the liquid formula, PB equal to H rho G, correct? If my PA, this is my PA, is equal to my PB, okay, my G is, let's use 9.81 meter per second square. If my G is 9.81, my rho of this density of this liquid is mercury, which is 13,546. So now I want all of you to calculate what would this height be if the vacuum is here and the atmospheric pressure is 101,300 Pascal. Can you now all of you go and calculate what would this height be? Can all of you do that now? I'm also doing it together. Okay, so can you all do that? Tell me what's the value of the height? All of you. Okay, measure the height. If I use mercury, what would the height be? The height of mercury. Liu Shixuan, value has no meaning if there's no unit. Okay, so can you write down the unit? Okay, Hao Ming, well done. You share the answer with everybody. Okay, Chen An and Ray Hong, are you able to get the answer? I already given you the formula, PA equal to PB, which is this one. Your rho is this one. Your G is this one. So what will your height be? Okay, so as what Hao Mi has mentioned to everybody, it is about 0.76 meter. So therefore, the question here says, if you use a mercury in this test tube, you need to be about 1 meter long. Okay, because the height here will be about 76 cm. Is that clear? Is that clear? Okay, so 76 meter is the same as 76 cm, which is the same as 7600 mm. So we can actually say that 1 ATM, okay, 1 ATM is equal to 1 ATM is equal to about 76 cm Hg. Okay, these two things are the same. Okay, this cm is not the unit for 76. Is this whole thing cmHg is the unit. Okay, in this case, cmHg, can you see here? cmHg is the unit of the atmospheric pressure. Okay, so you must see them together. Okay, it actually means you actually have a height of 76 cm of mercury. So 1 atmospheric pressure is about 76 cm Hg. Okay, now, just for practice, if I would, instead of use mercury, I use water. Water is 1000 kg per meter cube. What would the height be if I use water instead? So can you all calculate now? If I were to use water instead, what would the height be? How long the glass tube will need to be if I were to use water? So can you all calculate now? Hello, are you with me? Shishan cannot be even shorter, right? Mercury already 76 cm. How come water become 13 cm? So use the same formula. 101300 equal to H 1009.81. What will H be? Okay, in this case, let me get some answer. Chen An, why you leave your answer with mm? Can use meter. But your answer is correct. Chen An, well done. Wei Hong, how about you? Okay, so if you were to measure, you not measure, you could calculate, you'll get 10.3 meter. Is that clear? 10.3 meter. So 1 atmospheric pressure is about 76 cm Hg. It's also about the same as 10.3 meter water. So your test tube need to be longer than 10 meter just to measure the atmospheric pressure pushing down on you at sea level. Okay, so it's just like you, okay, it's just like you 10 meters deep in the water. That, okay, 10 meters of water above you is similar to all the atmosphere air above you. Is that clear? I repeat myself again. All the gases and air above your head, all the way to the end of the atmosphere, is the pressure acting on you, on the head, is equivalent to you being 10 meters deep in the water. How many of you can take it? When you dive in the water 2 meters, wow, you feel the pressure really a lot. Can you imagine when you go down 10 meters deep, the pressure acting on you is double compared to you above water. Clear so far? Okay, so can you imagine the deepest part of the sea is how deep? So every 10 meters is 1 atmospheric pressure. If your sea is 100 meters deep, you are at the bottom of the 100-meter sea. You're actually subjecting your body to 10 times the atmospheric pressure compared to it on Earth. And 100 meters is considered not deep at all. You know, our sea, our ocean is much, much deeper. Okay, it actually goes down as deep as 10 kilometers deep. So can you imagine those who want to go and find the shipwreck who are down at the seabed? They need special equipment just to actually go down and will not get crushed by the water. Yeah. So can you imagine that? Okay, so let's finish up the lesson, the theory. So today is a lesson useful so far. Okay, the last part I'm going to talk about this. Okay, so if both part is exposed to atmosphere, this atmosphere, this atmosphere, okay, these two lines should be the same. Okay, these two points should be on the same line. They have the same pressure. However, okay, can you see this? How do we do this question? Everything on the same line has the same pressure. So can you see here? B and C has the same pressure. So can I say that? Okay, let me make it bigger. Hold on. I'll make it bigger. Okay, so can you see here? Okay, point B here. Where? Change color. Point B here and point C here lies on the same line. Can you see that? So they have the same pressure. So can I conclude that pressure at B is equal to pressure at C, which consists of this one, pressure ATM plus this height here, H rho G, equal to the pressure at C. Okay, so can I say that pressure at the atmospheric pressure plus the height of this liquid is the same pressure at C. And then because B is the same as C, can you see here? Because pressure at B can push the water up here. So this B has greater pressure, correct? And this pressure is how much? This pressure is a combination of these two together. Is that clear? It's the atmospheric pressure, P0, plus the pressure due to this liquid above C. Because B and C are of the same height, and this liquid is not enclosed. Okay, this liquid is not enclosed. Okay, so on the same level, they're the same pressure. Anything below here is greater pressure. Anything above here is lesser pressure. Okay, but given the same liquid at the same level, they'll have the same pressure. Is that clear? Okay, so I will end the lesson for now. Okay, we'll go through a lot of practice next week. Okay, so I hope today's lesson has been of use to you. Okay, before I let you all go, I have some exit question for you, and I would like Zixuan to stay back for a while. Okay, let me give you the three exit question, the few exit question. What's the formula of solid pressure? What's the formula of fluid pressure? What's the formula of density? Okay, question number 4. How much you learned today? Your rating of 0 to 10. And number 5, how well Mr. Chu teach today? Okay, once you have written all your answer, I call your name, you may leave. And Zixuan, so stay back for a while. Okay, thank you everybody. Have a good night.